Getting new tires on the Dodge Ram today, and you know what that means. Tires are pretty bald. They are about to become more bald. Hey, welcome back everybody. So today we are back on the LS1 build. I know it's been a while. Things have been crazy. So just a couple of things that we did on this is we went ahead, of course in the last video you saw us strip the block and everything. So I took it down to the block shop and I ran it through the jet wash and the chemical cleaner. And I also machined the cylinders, got that taken care of, and got the block back up here. Now, as far as some of the internal parts on this, a couple things. Number one, when you guys are putting these things together, a couple of things about the early gen. This is a 2001, something like that. It's a 378 casting. So this would be the earlier LS1. Let's talk about the head bolts for a second because this is kind of an issue. Now let me clarify this by saying I know personally a lot of guys who've actually reused these factory head bolts, rebuilding these things successfully, okay? However, I'm not going to do that because the reality is, and there's no way to get around this, the head bolts on the LS1s are what we call a torque to yield bolt. Torque to yield is a different kind of fastener. It has rolled threads instead of machined, and it has a narrower area up here on the bolt. These bolts are actually designed to stretch as you yield them. And the reason that they do that, and this is not new technology, torque to yield bolts been around for, I don't know, decades. But really the aluminum engines or the bimetal engines especially, where I have a cylinder head expanding more than the block, with conventional bolts, what was happening in the early days when we started getting into bimetal engines, especially with the imports and stuff, the head would expand and contract and expand and contract, and the conventional bolt would expand with the head, and eventually they'd stretch and then they'd lose their clamping force and pop the head gasket. The torque to yield bolt is designed to be yielded or stretched to almost its limit when it's torqued, and what it does is it holds that clamping force during thermal cycles on the engine. And they're great bolts. They work fine, and they do hold clamping force better than a conventional bolt. However, one of the issues with them is the manufacturers all say, hey, one-time use. Once you yield those or stretch those, don't put them back in there because they can fail. Well, like I said, I know a bunch of guys that have reused these with no problem. So you can get, generally speaking, you can get more than one use out of them. But just because of the way I do things, I would recommend upgrading to this. This is what we're going to do. We're going to replace the head, the torque to yield fasteners, with a set of ARP studs, or I'm sorry, they're bolts, they're not studs. And it's really a much better quality fastener anyway, especially if you're going to put the screws to this thing and pound it, you know, in some kind of a hot rod or something. This engine here is geared a little more toward the hot roddy side. The guy wants something with some more power, so we're doing a cam upgrade. We are using the stock heads just for budget purposes, but they actually run pretty good with the heads. I think they're 241s or something like that. They actually run pretty good as long as you get a good cam and stuff in them. And so anyway, the LS platform is really good. I've talked a lot about it before. And so, yeah, we're going to build this turkey. The connecting rods, I am not going to use the old rods. We got a set of new connecting rods. These are, they're an OEM rod. It's a powdered metal rod, and they are forged. Now, the way they make powdered metal rods is they actually take metal powder. A lot of people don't know this, but they take metal powder. So they grind metal or steel down into very fine iron filings. It's literally, you can walk over to the hopper where the metal is, and you can scoop your hand in there, and it literally runs through your finger like sand on the beach, right? So it's ground up metal that's very fine. One of the advantages to powdered metal manufacturing, and again, powdered metal manufacturing is not new. It's been around for decades, right? It's not a new thing. One of the advantages is they can come out with new types of alloys, hybrid types of alloys. So in other words, an alloy is a mixture of metal. That's how we get forged components. We mix different, we have metals that have, on their own, they have really good properties, but when you add them together, they make a really strong part. So the powdered metal process it has an advantage, because a normal alloy, forging, what they do to make the alloy metal, and then of course once they make it, they forge it and they beat it into shape. To make that alloy, they got to heat the metal down, liquefy it, and then they mix all these metals together in a furnace. Well, there are some metals out there that they have really good properties on their own, but when you melt them down and try to put them together in a furnace in a liquid form, yeah, they don't like each other. They don't mix well, right? So they kind of repel each other. So there are certain metals, I mean, with the conventional forging process and the alloy process, there are some limitations on what metals will mix with each other. With powdered metal, we don't have that issue. We can grind up any metal we want, and we can take the powders, mix them together really well, and they don't repel each other. They're actually all part of the same, and then they take and they have a mold that's the shape of this rod or whatever part you're making, and they put this powder in there, and there's a big ram that comes down and puts like a 200,000 pound press head on this thing and combines that metal together, and then of course they go through a multiple stage heat treat process, and then they make that as one piece. And of course, most of you know this is what they call a cracked rod or a fractured rod. The parting line here is a break. They make this all as one piece, and then they have a machine that breaks the cap off, and then they machine it and put cap screws in it. That makes the parting line a break, and that gives a much more uniform bore here, and it actually increases the surface area of the rod to cap where they mate. And the other thing is, I don't have a machined surface here, so the cap doesn't really move around. It really is a superior technology. And the thing is, I would say like probably 90-95% of the modern cars on the road today, from every manufacturer, are using the powdered metal process. It is a forged rod, and they are very strong. They're actually about 25 to 30% stronger than conventionally forged rods. There are some people that have hated on these rods. One of the problems Ford had with their Power Stroke is when they put powdered metal rods in it, they had failures. But that wasn't because the powdered metal process is terrible. It was just because that rod wasn't a good design. So physically, the dimensions of the rod were not adequate for the Power Stroke. They tried to lighten it up and all kinds of stuff, and that was not you don't want to lighten up your parts for a diesel. So all right, anyway, so brand new set of GM powdered metal forged rods. We're also replacing a bunch of stuff on the valve train. We got a new set of valves here. They are the factory size, which is a 2-inch intake and a 1-inch 550 exhaust. The heads, I'll have the heads over here in a little bit. I'm actually, my helper is machining them for me right now over at the other shop. They weren't, the heads were not warped at all, but they did have a little bit of pitting in one area, not bad, and it wasn't near the fire ring. So we're just going to go ahead and do a CBN mill on those and get a good finish so our head gaskets won't have any troubles. Now on the back side of the block, and also another thing we did, we final washed this. It's ready to put together. We final washed it with soap and water, and we also put the cam bearings in. I don't really think I need to demo that. I've got tons of videos doing that. It's pretty straightforward. And most of the time, most of you guys that are doing this, the machine shop's going to do that for you anyway. Now, on the lower end, it is perfectly acceptable, contrary to what some people have told you. If you actually get the information from GM, you find out that the main bolts on the LS-based motors and a lot of their engines, these are not torque to yield bolts. They do require a certain amount of torque and a torque angle, and I'll show you that when we put it together, but these are not torque to yield, and GM does not require or specify that these need to be replaced. You can reuse these. So they do require the cross-bolted mains bolts. The cross-bolted main bolts go in here, and they do recommend that you replace those, mainly because they have a sealing washer on them. I'm going to go ahead and do what GM recommends on this, because we want this thing. Those engineers, I hear a lot of people, oh, I used it successfully with no problem. Yeah, but I kind of like what the engineers tell me to do. I listen to the engineers, and they do tons and tons of R&D, and they see a lot of motors come back for one reason or another. When they recommend that you replace something, I usually go with their recommendation. I'm going to go ahead and go with what GM says. So you can do what you want. I know guys that have reused those side bolts successfully, but I'm not going to do that. All right, so I got the master kit sitting here with all these brand new shiny parts, and I'm going to kind of walk you through that before we put this turkey together. Okay, so my guy just finished milling the heads. We still have to cut the seats and seat the new valves in there, but these are the 241 casting. They're a halfway decent performer. It's not, I mean, you can get much better heads for this. They have the cathedral ports, of course, which is far superior to the early small block, and they actually flow pretty good with a 2-inch intake and a 1-inch 550 exhaust. The one nice thing about these heads is all of the ports, unlike the earlier small block and even the big block Chevy, all of the ports are mirrored. They're all exactly the same. So they all have the same exact shape, and they all have the same exact port design. So every cylinder gets the same amount of flow. The other thing is, if you remember on the old small block, they had the 2 exhaust valves here, and there would be a lot of heat here. There'd be major heat in the center of the head. They've separated all these, and they've gotten these 2 exhaust valves away from each other, which is actually a better design. It's more like a Ford. Ford's been doing this for years. So, but a fantastic cylinder head design, and like I said, you can get a much better head for this, but these are decent. This will be a decent builder. I still need to get these over and cut the seats and get the valves seated. These have a beehive spring from the factory. Now, I don't have the springs for these yet because honestly, I don't have the cam either. When I first started this, customer wanted a pretty radical cam, and then he called back and he's like, no, I want to back off on that. I still have to have another phone conversation with him about just exactly what cam we're going to put in here. We're not going to go stock. We want to upgrade it and make it so it's pretty potent, but he doesn't want a real radical cam. He wants a fairly smooth idle, but I'm sure there's a lot of options out there, so we can make this work pretty good. So but we have to match the new springs to the cam. We're definitely not going to reuse the old springs. So that is where we're at on the cylinder heads. I'm not going to do a really in-depth cylinder head assembly and rebuild and everything, because I mean, most of you, when you do this, you're not really going to be doing the head work yourself. You're going to send it to a machine shop. And I've got tons of other videos where I'm cutting seats and guides and all that stuff. So So now let's take a look at this engine kit. These are the parts we got. First of all, our pistons. We went with a sealed power piston on this thing. And this is a really nice piece. It's got the coated skirts, and it's a flat top piston. These are lightweight pistons. They're pretty good. This is a hyper-eutectic piston. We went with rather than just go with a plain cast like the factory has, we put a hyper-eutectic in it. We were going to go with forged, but for this power level, it's just not necessary at all. A set of rings from Hastings. Now the nice thing about the rod bearings on the LS is it's the same as the old small blocks. 2" 100 is the rod bearing size, and these new rods we bought are a semi-floater, so we're going to have to put these in the rod heater and heat them in order to get these on. For most of you guys, that's going to be a machine shop thing that you have the machine shop do, but it's a press fit. The pin is actually larger than the bore on the rod, so we put these in a rod heater. I'll probably try to take some video of a couple of these when I heat these up and put them on. But that's the deal with the rods and the pistons. Very nice piston. And then of course we got a new timing set for it. Timing chain and gear set. New crank gear. The plug kit just consists of there's only a few plugs in this thing, but they're all threaded and screw in, so that's one nice thing about the plugs on this. And then of course the oil pump. We got a new melling pump for this thing. There are a couple of seals that come in here that you have to use for the pickup tube. That is our brand new melling pump. When it comes to oil pumps, man, don't reuse the old one. That's my advice. So always put a new pump on this thing. So this is a G-rotor pump, which is what they use, goes on the front of the crank. Melling is a good brand, we like those. And then of course we talked about the head studs earlier. And then we have the main bearings. Now the main bearings are not the same as the old small block. It's a different size. It's a unique bearing, and of course we got sealed power performance main bearings for it. And that's really it. I mean, like I said, the LS is a pretty simple motor. There's really not a lot to it. There are a few things that you have to know as far as aligning the front cover and the rear cover. That's actually one of the biggest learning curves if you've been doing older motors, is actually getting the front covers aligned and the seals in correctly. It requires the use of special tools. I mean, you can do it without the tools. You can use a straight edge and so forth, but I actually use the GM tools because I want to do it right the way GM says to. So yeah, that's really it. Next, I'm going to get these rods and pistons together, get the block up on the stand, and oh, the crankshaft is over there too. We cleaned the crankshaft and polished it. You'll see it when I put it in. That thing's heavy. I'm not going to grab it and drag it over here. So I'll get this block up on the stand and we'll continue. Okay, so now the next step, you guys, is to get the main bearings in here. And we want to check our oil clearances. This is something you don't want to skip. Man, I love these blocks. I mean, they also, like the 5.3 and the 6.0 is a cast iron version, but I was thinking about the earlier small block. And don't get me wrong, I'm a big fan of the early Gen 1 small block, even up to especially into the Vortec era. But you know, when you really delve into the LS motor, the LS engine, and you start building these things, I've never really done a video on the LS before. I started a 5.3 build. I still haven't finished that stupid thing. But regardless of that, I've done, man, I can't even count how many of these engines I've done over the last 20 years. 100. I never really put one of these on my channel mainly because everybody was doing them, and I kind of, when I started my YouTube channel, and even right up until recently, I kind of wanted to stick with older vintage, my vintage iron. I wanted to do vintage stuff that nobody was doing. But I've gotten so many requests for an LS that, you know, and this one came along, customer wants it done, so that's why we're doing this. But you know, the thing is, the more I think about it, every time I do one of these blocks, I'm just struck by how good the architecture is, you know. And there's always those guys out there, it's like, oh, aluminum is terrible, if you overheat it once the motor's junk and this and that. And you know, there's some truth in that, but man, I'm telling you, the architecture of this aluminum block, the LS1, it is so strong and rigid. It's phenomenal. The skirted block design, and the 6-bolt main caps, the forged main caps, the captured gasket technology for sealing is just incredible. Steel, the Nickel coated steel sleeves, that's the other thing. Like on the old small blocks, you see one with 150, 200,000, you got that big old ring ridge up on top of the cylinder, you got all kinds of cylinder tapering out around. With the Nickel coating and the hardened forged steel sleeves that they're casting into these blocks, I mean, I've seen these things with 200,000 on them and they still got the full crosshatch in them. There's no ridge. You rarely got to bore one of these, even with high mileage. And that's one of the reasons, like, guy, you can go to the boneyard and find one of these cheap, you know, with 150K on it. And you can turn it into a street rod motor without doing a lot to it, because the cylinders are still good. The cranks are good to 1,000 horsepower. You know, that old 442 cast crank that's in the early small blocks, try putting 1,000 horsepower through that crankshaft and see what happens. But that's no joke. The stock LS crankshafts will take 1,000 horsepower all day long with no problems. It's not uncommon to see one of these blocks pushing 700, 800, 900 horsepower, 1,000 horsepower with no problems. I think the 6.0 block, which is a cast block, is a little more rigid than the LS1 block. But I mean, you know, I've seen these things 700, 800 horsepower, no problem, and they live. So the block design is phenomenal. I'll put the bearings in here in a few minutes, but the skirted block design. Now on the early small block, the pan rail is way down here, and the caps are just all by themselves out here. They don't have any support from the block. So this block is so much more rigid. And you know, this block design is not new. This isn't something Chevrolet came up with. If you look at the big block Chryslers, the 440, the 383, the 426 Hemi, they all have skirted blocks with captured main caps. The old Fords, the 427, the 390, the 428 Cobra Jet, those engines all skirted block, and those things, I mean, they use them for endurance racing and all kinds of stuff, and they're just fantastic blocks. The architecture of this block is just amazing. The way that the lifter bores, the way that they're supported with all this webbing, and they're down here in the thick portion of the block, there's a lot more support for those taller roller lifters. The camshaft is huge. So this cam billet, and this is the old cam, we haven't got the new one yet, but the diameter of the cam journals is just way bigger. And that allows us to have a much bigger lobe here, a bigger base circle. And the advantage to that is you can run a much more radical cam, and it's a lot easier on the valve train because you don't have this crazy up and down shock. You got a lot more base circle to come off of here. So the shocks that the valve train takes is diminished greatly. And that's, you know, one of the reasons that they did this. The engineers, when I look at this block, everything that was wrong with the old small block, and again, I love the old small block Chevy, I'll probably never stop building them. But it's almost like the engineers looked at that and said, okay, we want to fix everything that's wrong, all the shortcomings and deficiencies of this early, you know, this technology has been around since 1955, and they did it with the LS1. They cured all the problems. The other thing is, the heads aren't on this right now, but one of the things that is really a big advantage is the intake manifold on these. They went with a plastic intake, and I know a lot of people bag on that, but the amount of of heat dissipation and the lack of heat sink that gets into that manifold is incredible. That's one of the reasons they did it. Also, the cooling system, now you know on the early small block, the cooling system runs through the manifold, runs through the intake manifold. On the LS motor, the cooling system isn't anywhere near the intake, so we don't have all that engine heat being soaked into that intake manifold. So the intake is basically separate from the engine, and it keeps that air charge just super cool. And then you add to that the big cathedral ports and the ports that are exactly the same as far as their dimension, the spacing of the valves and the placement of the valves, getting the two exhaust valves away from each other. And I mean, this motor is just fantastic. It is, when it first came out, I'll be honest with you, for a long time I was dead set against aluminum engines, years and years ago. But then my buddy built a twin turbo LS1 making 900 horsepower, running on pump gas with a mild cam that was chill, and your grandmother could literally get in that car and go get groceries in it. And I was sold. And that car lived. He's still driving that car. It's been 10 years. And if you're in a situation, you guys, where you're like, man, should I build an early small block or should I build a LS? As far as I'm concerned, it's no contest. If you can go LS and you can get 5.3s, which is an iron block, you can get 5.3s, they're a dime a dozen. Making 400 to 450 horsepower with a 5.3 is no problem, right? That's something you can do at home in your garage all day long. Cam swap, get some better heads, you know, do some upgrades to it, and you got to really, and not only that, you got fuel injection, you got the coil near plug technology. Think about a distributor. It has one coil. That coil has to energize and de-energize for every single cylinder, right? When I have one coil pack for each cylinder, I can energize and de-energize that particular coil for that cylinder firing. I only got to do it once every 720 degrees, right? So instead of the coil pack energizing and de-energizing every 90 degrees to fire every cylinder, each cylinder has its own dedicated coil with a lot more time to energize and de-energize, right? So you get a much more lively ignition system capable of much higher RPM and a hotter spark. So and you can run these things with an MSD box. They have an MSD box that'll run it. You don't have to have the computer. You can put a carburetor on one of these things. That's another thing I hear from a lot of guys. Oh, I don't like that electronic stuff. You can run an LS motor with an MSD box and a carburetor. You still have the coil on plug, and you have MSD ignition. So you don't have to run the factory fuel injection and the factory computer. Guys been putting MSD boxes on their race cars for years. It's the same thing here. So you could have yourself a killer street motor with a big Holley 4-barrel and a set of headers. That is just an absolute animal on the street. And the block is strong and rigid. It's just an amazing engine. So we're gonna get into this. The next thing I want to do is lay the crank in the engine. But before I do that, we're putting all new parts in this thing. We definitely want to check our clearances, so let's get started on that. Another thing about this block, you guys, you might see these holes here that are bored all the way through there, and you might wonder, what did they do that for? That is actually to help balance out the crankcase pressure so it doesn't build up in here. And also most of the crankshafts on these are gun drilled too, to relieve crankcase pressure. It gives that pressure a way to equalize itself in there, and it really does help. So let's look at our front main here. We want to check our main bearing clearances. Now I'm going to check them all, but I'm just going to demo this on one, and I know you guys have seen this before, but it bears repeating, because if you skip any of this, there's a chance that you could have clearance that are wrong. It's not likely, but it's possible. So you hear people say, oh yeah, my boater is balanced and blueprinted. So yeah, we got this balanced. Everybody knows what that is pretty much. But blueprinting is the process of measuring everything and documenting it, making sure it's right. So remember, the bearings that have the groove and the hole in it is what goes into the block here. And honestly, you can't really put the other one in because the locating notch is in the wrong spot. So we're just going to go ahead and put our standard bearing in there. Of course, we're going to take our #1 main cap and do the same thing, so that you'll notice that the upper bearing doesn't have any holes or anything in it. Now you want to make sure that this goes in the right orientation. The bearing tangs, the bearing notches, go to the same side. 2.559. I mic'd the #1 crank journal, and I got my mic locked here. So this is the size of my journal. Now we take the dial bore gauge here. This is our dial bore gauge, and I've got the correct tool set up in it, so I'm in the range of this. So what I'm going to do is I'm just going to take and I'm going to put my bore gauge right between the fingers of the mic, and with that in the fingers of the mic, what I'm going to do is I'm going to zero out my dial indicator. So it's about right there. So I'm going to go ahead and put this mic in here. You can't see that, it's down below the camera, but I'm going to put the mic in and try to duplicate our crank size. So you can see I'm off 0 there. I need to move that a little bit. We want to fine tune that because we want to duplicate the size of the crank. Okay, if you see that, let's get that back in there. Hopefully there's not too much glare. Let's see. So right there, I've got the fingers of the mic right down here on the bore gauge, and with the bore gauge we have got that, let's get it straight here, we've got that zeroed out. So what I've done here, guys, is I have mic'd the crankshaft and locked my mic. 2.559 is the standard size, and that's exactly, believe it or not, what that mic is reading. It's what it measured. And then we went ahead and with the mic set up here, we zeroed out our indicator. So the 0 on the indicator represents the crankshaft size. I know some of you guys use plastic gauge, and plastic gauge is okay. Personally, I don't like it, but that's just me. You can, and it works, but it's just not as precise. So now we've got our main bore here. Now remember, the crankshaft is going to ride inside there. The clearance between the crank and the bearing, in other words, the crank has to be slightly smaller, and the clearance is what actually establishes oil pressure, because oil is pressure fed in here, and that clearance is critical because what creates the oil pressure in the engine is the clearances. It's like a garden hose. So if I had a garden hose here and I was holding it, and you were across the room and I just turned and went, ha ha, you know, the water would just be like running out on the floor right here. There's plenty of flow, but there's not enough pressure. So oil pumps, the oil pump in your engine does not create pressure. That's a misconception. A lot of people think, oh, I need a high pressure pump because, well, no, what you're getting is you're getting a high flow pump. Oil pumps, conventional type oil pumps on these OEM engines and most engines do not create pressure. They never have. So there are certain type of hydraulic and oil pumps that create pressure, but the engine oil pumps for the most part don't. Now when you start getting into dry sumps and stuff like that, that's a whole nother deal. But when you're talking about stock type wet sump pump, not a dry sump, with an internal pump, the pump is usually internal in the block. Some are external, like a Mopar big block has it outside, but still it's a wet sump system. We have a pickup screen submerged in oil, the sump is the pan. It's wet, it's not a dry sump. Dry sump is high-end racing or high-end, high-end luxury cars, exotic cars. But for the most part, you're dealing with a wet sump, which means We got this big oil pan down here. We got this pickup tube down here submerged in oil, and it's sucking oil up in. The pump creates negative pressure up here, low pressure, and it sucks oil into the pump. Now the pump has an output side, and the output side of the pump does not create pressure. It creates a flow of oil. In the case of the LS1 and LS motors, it creates a massive amount of flow. They got a lot of oil capacity in these engines, which is a good thing. Now what happens is this big old large tube with this big massive amount of oil flowing to the pump, all of that oil that comes out of that pump on the exit side of the pump, this pulls it into the pump out of the sump, and on the exit side the pump is bolted to the engine, and it puts the oil into the oil gallery system through a hole in the front of the block right there. These clearances that we're talking about on the engine, the reason that the oil clearances on the crankshaft and the camshaft and some of these other bearings is so important is because those clearances are what are establishing the oil pressure. The manufacturer determines what that clearance should be based on their pump output and based on the needs of the engine to supply the right amount of oil pressure. So that oil gets into these, it's pressure fed to the crankshaft. So the crankshaft is in here, and there's a very slight amount of pressure. So what happens is the oil is pressure fed through that hole, and the rotation of the crankshaft pulls that oil around the crank, and the crankshaft actually separates from the bearing. When you have the oil clearance is right in the correct amount of oil pressure, while the engine is running, your crankshaft is never actually touching those bearings. There's a film of oil that separates it. It's called a hydrodynamic wedge. That's a fancy way of saying it's a liquid moving wedge of oil. But as that is running, now also the oil is blasting up through this hole, and it hits this clearance here, and the crankshaft clearance, it is resisting that flow. So the oil, what happens is it starts to back up in the gallery. So there's an oil gallery that feeds this. The oil starts to back up in the gallery, and it backs up all the way back to the pump. And what that does is that oil, that clearance there actually creates pressure. Pressure builds up in the system. So the resistance of this clearance to the large flow of oil is what creates pressure. Now, it stands to reason that if I get the wrong bearings in here, or I get my clearances wrong, it could cause low oil pressure. In fact, one of the most common reasons for low oil pressure on an engine is worn out rod and main bearings. When these clearances get too big here, now I have less resistance. The oil's just pushing out past it because it's all worn out. I have less resistance to flow, and it causes it doesn't back the oil up to the pump with as much resistance, and the oil pressure goes down. The pump is still putting out as much oil as it ever has, but it's the clearance that creates that pressure. So when we talk about measuring bearing clearances, this is a critical check. I mean, if you got this wrong, you could put a motor together, and I've seen guys do this, and they have little or no oil pressure. Let's say you have a crank that's ground 10 under, and you put standard bearings on it. Instead of 2 thousandths or 1.5 thousandths clearance or whatever, you got 12 thousandths because you got a 10 under crank. You know, you're gonna have like 3 pounds of oil pressure at idle, and maybe 12 pounds at full throttle. And the guy's scratching his head going, what the heck's wrong with this thing? All right, let's just put this bore gauge in there. So I'm going to go ahead and put my gauge in there, and I'm going to read it at the smallest point. During my clearance, I am reading 2.5 thousandths clearance, which is right in spec. Okay, 2 to 2.5 is where we want to be. So remember, the 0 is the size of the crankshaft. The bore, at my smallest point, the bore is 2.5 thousandths larger in diameter. Now, that might look like a lot, but it's not much. A human hair is 4 thousandths. A human hair is 4 of those graduations. So a human hair is over here. That's a little more than about half of a human hair. And that is actually the clearance that's specified. Now, I am going to go through and check all of these, but this isn't something you can skip. So if we go through and we got 2.5 thousandths on all those bores, we're happy, because that's exactly the amount of clearance that we need to get good oil pressure and get enough oil in there and keep the crankshaft from flopping around and all that stuff. Okay, so my battery's going dead, but I'm going to get all the clearances done, and then we're going to go ahead and we're going to talk about laying the crankshaft into this thing. On the LS1 pistons, the notch or the mark always goes to the front of the engine. And unlike the earlier small block, where you have 4 rods on one bank one way and the other 4 rods the other way, LS1 rods all go in the same direction, and that is the flat spot. If you look at on the factory rod, if you look at the rounded area of the powdered metal rod, and one side is a flat spot, the flat spot always goes towards the front of the engine. So we want the flat spot here on the rod, this flat spot, to match the notch. So the notch is going to go in the same direction on the piston, that notch, as that flat area. So we put them all on the same way. Now again, we talked about the fact that these rods are, this is our rod heater here. These rods are full floaters. So we've got our coils heating up in there, and we have to heat the rods to about 330 degrees. The machine has a thermostat because we don't want to overheat them. But we're going to put the notches on the piston toward the machine, and then we're going to pull the rods out and put the flat spot toward the machine, and they're all going to go on the same way. And these are, like I said, these are brand new rods from GM. The pin will not slide in, it's a press fit, so the pin is actually slightly larger than the bore, so it's a semi-floater. It floats in the piston here, but it's pressed into the rod. But we can't really press this together on a press, it'll damage the piston. So we have a connecting rod heater, and then we just very carefully slide the pin in. Now you got to be quick. This is a machine shop operation. This is actually not a simple process. It takes a fair amount of skill. You got to get this in quick. If you go too slow, the temperature will, you'll lose it, and the pin will get stuck halfway. So I think these are ready. So we're going to take it with our flat spot away, take our pin, and we're just going to slide our pin all the way up against the stop. And now it's tight right now, but once that heat radiates down, what's going to happen is it's going to loosen up. There it goes. And that is your semi-floating connecting rod. That rod's pretty hot right now, so we'll set it aside. But that's how that's how we hang them, and that's how the machine shop will do it for you. Facing the same side. Just very carefully slide our pin in against the stop. And we are in business. We're going to go ahead and put the next 2 in and get them heating. And that's it. That's how you do your semi-floating piston pins. Okay guys, so another thing we did is we set the heads up on the machine and we cut the seats, and we're going to go ahead and lap the valves in. I always like to lap them in just to make sure I have a true seal there. I'm not going to do that on camera. We got plenty of videos. We got chips and stuff in here from cutting them, so we're going to have to also run these through the jet wash again after we lap the valves. And then we'll be ready to put the heads together. But like I said, I don't have the valve springs yet. I'm waiting on the final cam selection for that. But we're getting there. So we'll get the heads lapped and washed, and then we'll go back and start looking at that lower end and probably get the short block together.